Question 4 is coming from circular measure. The diagram shows the shape of a coin. The three arcs AB, BC, and CA are parts of the circles with centers CAB respectively. ABC is an equilateral triangle with sides of length 2 centimeters. Part A, find the perimeter of the coin. Okay, of course, for the perimeter, we just find the lengths around the shape, so we add them. Now, I can connect this A to C here. I can also connect also A to B here. Now, I'm going to make these lines dotted. Now, this one here is an equilateral triangle. So that means if CB is 2 centimeters, then that means AB is also 2 centimeters. SC is also 2 centimeters. Okay, so we have this center here, then there is this arc, there is a sector here. The center is this one, the same. And also here, the center is A, then you get this arc here. So all the lengths are equal there. Okay, find the perimeter of the coin. So the perimeter of this coin is going to be 3 times the arc length. Okay, the arc length. First of all, these arcs also are equal in length. Okay, now since this one is an equilateral triangle, this simply implies that this will be 60 degrees, which is pi over 3, even this one, and also this one, right? All right, now length of an arc is r theta, not so? So we shall have 3, then times r is a 2, then the theta is pi over 3. So we can see that this 3 cancels with this, and then we remain with 2 pi, as simple as that. So 2 pi centimeters. And then part B, find the area of the face ABC of the coin, giving the answer in terms of pi and root of 3. Now, to find the area of this face, I can say area of this triangle, which is inside here, then plus area of this segment, this one and this one. And those 3 segments are all equal. Or I can choose one segment. Let's say we are having, actually, let me just choose one sector. Let's say ABC, this sector here. And we take, let's say this one here. I can get area of that. Then from there, I add on the area of this segment plus the area of this segment. Okay, so that is what I'm going to use. Area of face ABC. This one is going to be equal to area of sector ABC, then plus, there are 2 segments that are left, so 2 times area of the segment. Okay, and area of the segment is area of the sector minus area of the triangle. Okay, if I have a segment here, I mean the sector, then this one here is the segment. So you get area of the sector, then subtract area of the triangle. You see that? Okay, so area of a sector is a half r squared theta. Okay, and then this one here being area of the segment is going to be area of the sector, which is a half r squared theta, then minus area of the triangle. And area of the triangle is a half r squared, then sine of theta. Remember, if you have a triangle which is not right angled, and you have this side, you know it, this side, you know it, and then you know an angle in between, so the area will be a half times this side that you know, times this side that you know, then sine of theta. Okay, so that is what I'm applying there. Now, let's continue. I can actually first simplify the whole of this if I want. Okay, you can see that this one is actually common. Okay, so I can say a half r squared theta, then there is, when I factorize it, this will be 1, then plus the 2. So that one becomes 3 over 2, right? So I can write this as 3 over 2 r squared theta, then plus, when this one multiplies with this, that 2 goes away, then we shall have actually minus r squared sine of theta. So they want it in terms of theta, I mean pi, and then root 3. Okay. Now remember the radius is 2. So 2 squared, and then our theta is pi over 3. Then minus, again 2 squared times sine of pi over 3. Then to simplify this one here, this 3 of course will go with this one. This is 4 divided by 2, that will be a 2. Meaning here we have 2 pi. And then this will be 4 times sine of 60 is root 3 over 2. So this one will go here 2 times, not so? So that means the answer is going to be 2 pi, then minus 2 root of 3. So it is in terms of pi and also root 3. As simple as that.